This video is about Coulomb's law. By the end of this video, you should understand the difference between kinetic and potential energy, you should understand Coulomb's law, and you should understand how potential energy relates to distance between particles. As you likely know, kinetic energy is energy due to the motion of an object. Kinetic energy depends on both the mass and the speed or velocity of the object we're dealing with. In this class, we'll be dealing with particles, so kinetic energy will depend on how fast the particles are moving and on their mass. We see this in the equation here, which shows that kinetic energy is equal to 1/2 mass times velocity squared. Potential energy, on the other hand, is due to the position of particles. One way to consider potential energy is to think about it as stored energy arising from attractions and repulsions between objects. In physics class, you likely talked about gravitational forces. They result in differences in potential energy for large objects. However, gravitational forces have negligible effect on objects as small as we're dealing with in this class. Therefore, we'll be focusing on the electrostatic forces that result in differences in potential energy for particles. These electrostatic forces cause attractions and repulsions between particles. When particles move towards or away from each other without changing speed, there is a change in potential energy. Recall that we said the potential energy was the energy related to position. Here, the particles are changing their position, but their speed remains the same. On the other hand, when particles collide and change speeds, there is a change in kinetic energy. Here we see one particle colliding with another particle, therefore transferring some of its kinetic energy. Notice that both particles changed their speed, therefore their kinetic energy changed. So, to summarize, when we have a change in particle position, we have a change in potential energy. When we have a change in particle speed, we have a change in kinetic energy. Now let's look more closely at this change in potential energy. Coulomb's law tells us that the potential energy resulting from the electrostatic attractions between particles is proportional to the magnitude of the electrical charges of the objects and inversely proportional to the distance between the objects. You won't have to solve this equation, but it's important to understand the implications of this equation. For our purposes, we'll almost always consider particles with opposite charges. Therefore, if Q1 is opposite in sign of Q2, our electrical potential energy will always have a negative sign. Therefore, as distance decreases, as the particles get closer to one another, our electrical potential energy will become more negative. In sum, then, as oppositely charged particles move towards each other, decreasing their distance, their potential energy decreases. Likewise, when the distance between them increases, electrical potential energy increases or becomes less negative. Looking at this graphically, here we see a diagram showing like charges on top and opposite charges on the bottom. First, consider what happens when Q1 and Q2 have a charge that's the same in sign, both positive or both negative. According to Coulomb's law, when this is true, the particles will repel each other. On the other hand, when the particles are opposite in charge, one positive and one negative, they will attract each other. As we said before, we'll be focusing mostly on oppositely charged particles in this class, so let's zoom in on that portion of the diagram. Take a second to consider the two questions at the left. What happens to the potential energy as the distance changes? Notice that as we said in the previous slide, as the particles get closer and closer and distance decreases, they will attract each other stronger and stronger. This results in a decrease in electrical potential energy. On the other hand, as particles move further and further away from each other, increasing the distance between them, the electrical potential energy will increase. So what does Coulomb's law mean to us? Well, as we said, we're focusing on oppositely charged particles here. So first, Coulomb's law tells us that oppositely charged particles attract each other. This applies to both oppositely charged ions and to atoms or molecules attracted by intermolecular forces. This also applies to atoms in a covalent bond that aren't charged in the way we usually think. We'll deal with this more when we talk about bonding in a later unit. As we said before, Coulomb's law tells us that as the distance between oppositely charged particles decreases, energy decreases or becomes more negative. An easy way to think about this is to consider the fact that bound particles, meaning particles that are strongly attracted to one another, are at a lower energy state than unbound particles, particles that are far away from one another. Likewise, as distance increases between these particles, energy increases. Therefore, energy is required to separate attracted particles. Conversely, energy is released when attracted particles come together. That brings us to the end of this video. Let's review our goals. First, we looked at the difference between kinetic and potential energy. Then we looked at Coulomb's law. And finally, we looked at how potential energy relates to distance between oppositely charged particles.